induced anomalous metallic state in the vicinity of the superconductor transition. Before I start, I would like to thank my collaborator and my former PI, Gaara Friedman, Martin Kolevsky from our group, Claire Marchetti from Paris-Saclay University, and Amitai Cohen and Ran Salem from NRCN. So let's do a brief start very quickly because we heard it multiple times in our in this conference.
You have to point to this.
I think it will be difficult. So when you go to the 2D limit, superconductivity is very fragile. We have this superconductor-to-insulator transition. Many tuning parameters have been investigated in the past, and we added one more tuning parameter to this list, which is the pressure. There are multiple ways to explain this quantum phenomena. One of them is the Bose-Insulator. One of them is the Bose model when you have a granular system, but not just actual granular systems can fit to this model. It can be seen that even in amorphous samples like amorphous indium oxide, which will be the main material we did our measurement on, show some electric granularity with adding disorder to the system. Electronic grains of superconductivity, island superconductivity emerge in this amorphous indium oxide, and thus giving us those granular grains of superconductivity. Nevertheless, even though this quantum phenomena was examined a lot for the past year, there are some open questions. One of them is something that we discussed many before. Is it a direct transition from superconductivity to an insulating behavior, as we see in amorphous indium oxide, or maybe even a bit more clear in titanium nitride, where we see only those two phases, or we have this metallic state, this anomalous metallic state, where we will call them M1 and M2, where M1 is the anomalous metallic state where we see a drop at the beginning and then saturation in the resistance, and M2 where we see at first initially increasing the resistance but then saturation, and we see the niobium silicon and many other systems. So when do we see it? When we don't? Why does this anomalous metallic phase emerge in some materials and others didn't show them at all? This is some open question. Some, of course, may argue that it's just an artifact of the measurement, just a noise that you put in your system, but we want to shed more light by adding a new tuning parameter to this phenomena, which was the pressure. Something that we didn't discuss before, what pressure can do to superconductivity. So the understanding of what exactly pressure will do to your sample is very, very complex, because pressure effect on many things inside your material, the photon energy, the band, the density of state, and many other things. So we can see the pressure do different stuff and different effects in every other material. Here we have those different component effects that the pressure can do to our systems. One of them is the destroying the superconductivity, where we can see it on superconducting metallic element. We have here a graph of normalized critical temperature as a function of pressure for multiple superconducting metallic elements such as lead, indium, tin, and more. And as you can see, they increase the pressure on those materials, on those superconducting elements. The critical temperature decreases, which indicates again pressure destroyed the superconductivity in those materials. This effect was explained by the fact that pressure reduces the density of states in those materials, and if you are reducing the density of states of the superconductivity, you're destroying superconductivity at the sample. On the other hand, on the much more hot-tech and maybe controversial topic, the high temperature superconductors and the race to get to room temperature superconductivity, where many papers emerge that shows that under pressure we can achieve higher and higher DCs. This is one that still didn't retracted on lanthanum hydride, and this is I think this won't be retracted at all. There are many experiments that agree on this phenomena. And under pressure, at least at the beginning, pressure enhances the superconductivity in those materials. The critical temperature increases. As you can see, up 150 GPa. The TC increases to up to around 250 Kelvin, which is pretty high, much more than lead, indium, and the other elements. And in those materials, the high temperature superconductor, the understanding of exactly what pressure is doing to the sample is much more complicated. It differs from material to one material to another. There are many explanations of what exactly pressure do, but from what I found in many papers, the main common stuff that came along is that under pressure, we couple different regions in the systems. Many of them, high temperature superconductors, are layered materials. You make the atoms closer and thus increase the coupling between the different regions. So many experiments was done on 3D superconductivity. We want to, the common way to do so is by diamond anvil cell. What is diamond anvil cell, or DAC in short? It's a device that contains diamonds that are deep, are cut off, and you can just put your sample in between them and just push one diamond to another, mainly with a set of screws. There are some other ways, and push one diamond to another, and you can achieve multiple GPAs in between your diamonds on your small sample, small compared to normal silicon substrate. And those diamond anvil cells was used a lot. There are many types of diamond anvil cells. Our diamond anvil cells are a pretty unique one. It's a miniature diamond anvil cells in the size of around, its diameter is around of €1 coin, so pretty small. It's made out of copper beryllium, which is a strong material, but also can enable us to cool down our samples. We need to be thermoconductive. We have to have good thermal conductivity so we can measure our thin films inside our organic measurement. And with rotating the screws by a few degrees, just a tiny bit, I can pretty easily achieve 1 GPa, which is around 10 to the 4 atmospheric pressure. In the beginning, when I started those experiments, it was a bit hard for me to understand exactly what 10 to the 4, 10,000 atmospheric pressure. So maybe a bit of a better taste what 1 GPa really are. We can take the much bigger Eiffel Tower, since we are here in Paris. We can rotate the Eiffel Tower upside down, and with all of its weight, 10,000 tons, in the tip, when it touches the ground, we will get 1 gigapascal. So from now on, when we see my measurement, instead of talking of 2, 3 GPa put on our thin film, we can say we stacked 3, 4, 5, 10 Eiffel Tower, one on top of another, on our diamond anvil cell. So those diamond anvil cells, there are, I think, thousands of experiments, but I think 99% of them was done on, or maybe all of them was done on 3D bulk material. We wanted to go to the 2D linear, to thin films. So for that, we needed to invent a new way to do so. So let's see from a video that I made. So we have our diamond anvil cell. After aligning my 2 diamonds, I open the diamond anvil cells once again, take out the bottom diamond out, and I grow my 2D thin films directly on top of the diamond. So my diamond is my substrate. By using a mechanical mask, first I evaporate platinum contact directly on top of the diamond from the culet, the flat area, to the bevel. Here we have a microscopic image of our platinum contact directly on top of the diamond. Afterwards, we evaporate our thin films, mainly indium oxide, again, through mechanical mask. Nowadays, we developed new methods with photography. So we evaporate our indium oxide in between the contacts on our diamond anvil cell. Here we can see our 2D thin films on top of the diamond between our contacts. And since we have another diamond that will go on top of it and pressurize these thin films to higher pressure. The thin platinum foil that we evaporate tend to break, especially in the exit area where the Q-let end and the bevel starts. Therefore, we want to ensure we can measure our samples continuously in higher pressures. So for that, we added platinum foil, thin platinum foils, thin platinum foils on top of our evaporated one, so we can ensure this conductivity. Lastly, we put our diamond anvil cell back in the DAC. We add ruby spheres, as we can see here, those tiny ruby spheres, to be able to measure the pressure inside our diamond anvil cells. The fluorescence of the ruby is very tunable by the pressure. And then we can close our diamond anvil cells once again. We have a picture of our final sample, and we are ready to go. We have those thin films in between the diamonds, and we can put the DAC and its and everything inside our helium-3 system, diffusion system, and cool down and see how the pressure affects our 2D films. So let's take a look on one of the samples. We started with 30 nanometers insulating indium oxide sample. We have here its log scale of equidistance, the function of temperature measurement, and ambient pressure. We start with an insulating behavior, and we can tune the starting point of the indium oxide of our film with our evaporation chamber. And I can start pressurizing my thin film, applying pressure on our indium oxide. We see the superconductor-to-insulator transition. We see the transition from an insulating sample to a superconducting one. And we see that we undergo the transition first time under pressure. I said first time because as we continue increasing the pressure even more, we start to see a destruction of the superconductivity. As we continue increasing the pressure, the critical temperature starts to decrease, up to a point where we cross the SIT once again. The sample goes back to being an insulating, the resistor doesn't drop anymore, and we go further into the insulating regime as we continue pressurizing the sample even more. Not just this sample, we took samples across all the SIT. It's different starting point, different critical temperature at ambient pressure. Pressurized all of them. We see pretty much the same results on all of our indium oxide sample. Those two competing effects. First, we increasing the superconductivity. We can see that at ambient pressure we have critical temperature spanning from 0, which indicates we're in the insulating regime, or up to 3 Kelvin. When we start our experiment, first we see an increase in the critical temperature, an increase, enhancing of the superconductivity, but after a certain point, we have a limit around 2 gigapascal, where the pressure starts to destroying superconductivity. We go back down with the critical temperature up to a point where we go back to 0 critical temperature, indicating we are once again in the insulating regime.
Is it reversible?
Yes, if you want to see it's somewhat reversible. If we have time, I can show you the reversibility graph. So after we saw this two competing effect, we saw that we also take a notice that in between this second time we go from the superconducting to the insulating state, those lines doesn't seem to go all the way down to 0, doesn't seem to go just to infinite, it seems to saturate. It might be even more clear when we look on a different sample, when we start in stronger superconducting samples under ambient pressure. We really see this saturation in the resistance in a finite value. We don't go to 0, we don't go to infinity, which indicates we have some metallic phase, both the M1 and M2 inside our indium oxide, which was very, very surprising for us because we measured indium oxide in our lab for many, many years, and we never saw this anomalous metallic phase in our indium oxide sample. Changing magnetic field, we're changing the thickness, we're changing the disorder. Never we observed these anomalous metallic states with other tuning parameter. Pressure was the first time that gave indium oxide the opportunity to be this anomalous metallic phase, and that fact that we measured our anomalous metal in the same system where we never saw this anomalous metal before was the first indication that this is a real effect on our sample. It's not just noise, because this system is never seen it since, never saw it before. It was noise-free systems, of course, never noise-free at all, but at some point. More things that we did to make sure that this anomalous metallic state is real is to measure our indium oxide sample in 2 different labs, in Israel and here in France, and we saw this metallic state in both of them. And one last thing that we did is that we took our metallic phases, and we have those 2 metallic phases, M1 with the resistance drop, M2, this is the start of the saturation, and added a magnetic field.
Excuse me.
Yes.
The vertical axis is square resistance or just resistance?
It's square resistance.
So it's below the quantum of conductance, well below the quantum of conductance.
Yes. It's harder on the higher temperature, but for my measurement, we are close to the quantum resistance when we changing from the M2 to from the M1 to M2, or from the M2 to inserting side. So when we added magnetic field to this mix, we see that this anomalous metallic phase disappears. We go back to a normal insulating behavior. We don't see the saturation anymore. Of course, it's gradually the resistance increases up to a point when it's disappearing, as well as in our M2 sample. The saturation disappeared. 4.5 Tesla, we see it even clearer. And thus, again, in the same cool down, the same measurement, nothing changes. Once we see our this metallic phase, we're adding magnetic field, it disappears. So we don't believe this is adding noise to our sample. It doesn't mean that we don't cool down the sample. We can reach the temperature. We see that we have good thermoconductivity. So we do believe we did saw this anomalous metallic phase first time in our indium oxide samples under high pressure. Last thing that, not last thing, but one more thing that we saw is when we take a look on our insulating side and we compare both the most insulating sample, the most pressurized sample, and the ambient one. Take a look in a zoom picture on both of them. And even before I analyze something, even before I say something, we can see that the 2 of them are fair from one another. The pressurized insulating state seems to be much weaker, even though its resistance in the normal state, in the higher temperature, is the order of magnitude higher than the resistance in the ambient pressure. Yes? In the ambient pressure, we can see that when we cool down our sample, we have the order of magnitude higher in the resistance. So trying to fit those two different insulating states, we see that in ambient pressure we have the body insulator where we saw it again and again under ambient pressure on disordered indium oxide sample. We have activation behavior, R goes as T2-1, but as we pressurize our sample, we undergo another transition from body insulator to another insulator, where we see a normal fermion insulating behavior under higher pressure. So try to understand what the pressure doing to our systems. So we took the model of the body model. We have those indium oxide sample with the different grade of superconductivity. Within each of them, we have superconducting wave function. And when we first apply pressure to our system, we enhance the coupling, we enhance the connection between those two different grains, and thus increasing superconductivity. As we continue increasing the pressure even more, we're reducing the amplitude within each grain, and thus we're destroying superconductivity in each one of them, and so superconductivity in the global system, up to a point where we destroy superconductivity at all, and we left with a normal Anderson insulator. And we think one of the most unique things is that in between this transition, where we increase the coupling and reduces the amplitude, we discovered this anomalous metallic state that was never been seen in indium oxide. This led us to propose our phase diagram, where we have those two different composing effects, competing effects, the coupling and the amplitude of our system, and the different phases. Let's put previous SIT work pretty quickly. When we take Bismuth and change the thickness, we see a transition from superconducting to Anderson insulator. When we take indium oxide with disorder, we see a change from superconductivity to a Bose insulator. Now in silicon, when changing the thickness, we see a transition that goes to all of them. And what's the common things to all of this arrow and to other SIT is that when you change this tuning parameter, you either destroy the amplitude, destroying the coupling, or destroying both of them, or enhancing both of them. You never see the increase of one when you destroy the other. The pressure is unique in that sense. It gives us a new direction to explore our SIT. We go with enhancing the coupling while destroying the amplitude. This new direction of arrow in the superconductor in this phase diagram, which also led us to go through those anomalous metallic states to see them in our indium oxide films under higher pressure. So we believe that to be able to see these anomalous metallic states in your materials, you need a sample that have low superconducting amplitude in the superconducting wave function, but also a good coupling between the different regions in your system. And with that, I would like to thank you and conclude my talk.
Questions?
Yes, how do you know how much pressure you actually apply?
So we have two different ways to do so. One of them is with ruby fluorescence. Ruby fluorescence peak is very, very sensitive to the pressure on it. So we just do spectroscopy and we can see where is the peak. The other way to do so is by Raman spectroscopy. Raman spectroscopy on the surface of the diamond, and we can see how the Raman spectroscopy changes with the effect of pressure, and we can see that even across our sample, how the pressure changes.
Thank you.
So there is a question. Benjamin?
I have two questions actually. The very impressive experimental work. I was wondering first, would you characterize the surface of diamond, which is not necessarily super flat?
Yes, we did do AFM to the surface of the diamond, here in Saclay even, and it's flatter than most of the silicon substrate.
Okay, because it's cut.
Because the machining of the diamond are super precise, because if you have a bit of a degree of a bit of unflattened area between your diamonds, one diamond will break the other. Like it's very easily to break diamonds. This is how the diamond looks after the experiment. You don't see the diamond at all after fully taking the diamond to the edge. So yeah, you need to be very, very precise in those machining.
Okay, for artificial diamond, the surface is very rough, but perhaps the natural one is good. Then I have a question also, which is about reversibility of the measurements. So my question is, how can you make sure that indium oxide is very easily crystallizes in many situations? If you want to go 60 degrees Celsius, if you irradiate with X-ray, if you want to make just simple X-ray characterization, or even E-beam electrolithography, you can change the material. How can we know that the pressure is not changing the structure and crystallizing or making something? Are you sure you come back to the amorphous initial state?
So yeah, this is a concern that we had, because pressure in many materials do this topological change. So this is the same graph that we saw before. And in this measurement, we did able to go down. And we can see that it goes back to this M1 phase when we see that decrease in the resistance. It's much different in the value, but the TC is pretty much the same. It's harder to measure because we lost contact in the way. So this is the 2-contact measurement compared to this 4-contact, and it's maybe not fully reversible, but the fact that we go back to some superconductivity, to some drop, indicates that we don't think it's.
You never get back to the blue curve or the white curve.
No, the white curve, it's in the ambient when I open my diamond emitter. Unfortunately, this is why it's also very hard, because when we cross the point where it's flexible, when we try to open the gasket, the medium inside just jump, and our indium oxide sample, part of it remains on the QLED, part of it jumps to the other diamond, and we have this abnormal sample. So it's really hard to say what's going back to the amorphous when we go to the ambient pressure. And no, we never go back to this superconducting side, but I do think it's somewhat reversible.
But it's not the TC is not the same.
Not exactly the same, no. It's even a bit higher. When you take a look on the 1.9 compared to the 1.4, the TC is a bit bigger. Yeah, somewhat improved superconductivity even, but it's hard to tell under not many experiments. It's going to pressurize and depressurized temper with
resistance. So you like C and resistance. Can you go back to same resistance value?
I never managed to do so, again, because I'm lost contact in the way.
Yeah, I understand.
It's very hard. Nevertheless, we are doing experiment now on niobium thin films, and maybe if I can say a bit of water on it, but in this sample, we managed to go back to see the same behavior. So indium oxide is one thing and niobium is the other thing, but niobium, we do see this reversibility very much very good comparison.
So unfortunately, I think we have to move on to the next presenter.